In this video, we'll discuss about polygenic inheritance. Polygenic inheritance is also known as quantitative. Quantitative inheritance means here we are talking about the quantity or number of genes. The example that we discussed to understand this is skin color in human beings. In humans, skin color is controlled by 3 genes, and these genes are written as A, B and C. And as we said, quantity matters. That means the number of dominant genes would decide how much of melanin would be produced. That means if all 3 genes are present in their dominant form, that means all 6 are dominant, that means maximum melanin would be synthesized. So here maximum melanin production would take place, and the color of the skin is going to be darkest. So here we consider that skin color as black. There can be an intermediate situation also. Both, or rather all 3 genes in their heterozygous form. So here there are 3 dominant and 3 recessive genes. So this is in between this extreme and the other extreme. Here the melanin content is going to be intermediate, and this skin color is also known as intermediate, or what we understand as wheatish. And the other extreme is all these genes, all alleles of these 3 genes are in their recessive form. And as there is no gene which is responsible for or regulating melanin synthesis, there is no melanin produced. So melanin production would be 0, and such individuals are known as albinos. So we have extremes, all 6 dominant, none of those dominant, that means all 6 recessive, and this is the intermediate. But we have a range between this and this also. 6 dominant, then there will be 5 dominant, then 4 dominant. These are 3, and we would have a range between this intermediate and this extreme. Here there are 3 dominant, so we'll talk about 2 dominants, then 1 dominant and 0 dominant. Now, to understand the color of the skin, let us have a key so that we know what exactly we are talking about. If there are 6 dominant genes, then the skin color would be considered as black. This will help us to find out the ratio when we plot the Punnett square. And let us talk about the other extreme, that is 0 dominant. There are no dominant. The skin color, actually they're white, they're called albinos. So this is albino. This is somewhere we are talking of the intermediate, so that means there are 3 dominant. And the skin color is written as intermediate. Now we have to go in both the directions. That means 2 dominant, then 1 dominant, here 4 dominant and 5 dominant. So these are the intermediate stages between the middle one and the extremes. This is intermediate, and now the dominant genes are increasing. So this individual is going to be dark, because here 3 genes were responsible for synthesizing melanin, here 4 genes are responsible. Then this individual will be very dark. Now let us come to the minimum numbers. This individual is going to be fair, because 3 dominant genes were giving intermediate or wheatish skin color. 2 dominant will give less in melanin production. So these individuals are going to be fair. Then next is very fair, and the last, that is our other extreme, is albino. So this is going to help us find the ratio. Skin color in humans is polygenic inheritance. This was told to us by Davenport. Davenport explained that skin color inheritance in humans is polygenic type of inheritance. So this is our key. I'm going to leave it here so that when we count the number of individuals in a particular skin color type, this key is going to be of great help. Now, say we are talking of pure one. And in most of the cases, we always start with pure line. That means all three in dominant form, that is a black individual, the darkest skin color is crossed with all recessive, that means with an albino. In this becomes our parent generation. In F1, the gametes produced by this individual would be one of this, that is A, one of B, and one of, it should be C. So one of A, one of B, and one of C. So all 8 gametes would be of the same type. Now here we are talking of 3 genes, so the number of gametes produced are going to be 8 in number. Here A, B, and C containing all 3 recessive. So in F1, when this type of gamete fused with this type of gamete, we get heterozygous. That means all 64 offsprings are going to be with intermediate skin color. Reason, they have 3 dominant and 3 recessive. We said 3 dominant would have intermediate skin color. Now, to find the ratio in F2, we will have to self these individuals. AaBbCc crossed with heterozygous AaBb and Cc. Now, before we actually plot the Punnett square, let us see the type of gametes which are produced by these kind of individuals. We know during gamete formation, out of one gene, one allele will come into the gamete, one out of this and one out of this. So let us talk about the various combinations which we have, and that would also help us understand why did we say that there are 8 gametes which are produced. So let us start with all dominant, capital A, B and C, all 3 dominant. Then let us come to 2 dominant. A, B dominant, C will be recessive. A, C dominant, B is recessive. B and C dominant, A is recessive. So in the first case, we took all 3 dominant. In next 3 cases, we took 2 dominant. AB dominant, AC dominant and BC dominant. The third one is recessive. Now, in the next case, we will take only 1 dominant. A dominant, B and C recessive. B dominant, A and C recessive. C dominant, A and B recessive. And the last is where all 3 are recessive. This gives us 8 possible combinations. 1, 2, 3, 4, 5, 6, 7, 8. And that is why whenever there are 3 genes controlling a particular kind of inheritance or showing a particular kind of inheritance, the number of gametes is 8. This we have to remember, and this is how we have reached to these 8 gametes. Now when we want to know the ratio in F2, these type of gametes, so 16, when we plot the Punnett square, we will have to write 8 gametes on this side, 8 gametes on this side, and we are going to get 64 offsprings. So our Punnett square is going to be a big Punnett square. So let us clean everything, and I'm going to just leave this key here because that will help us to find the ratio. Punnett square is going to be big. We have to write 8 on one side. And by filling this Punnett square, we will also talk about a shortcut so that we save time on all these things. So this is 1, 2, 3, 4, 5, 6 and 7. Let us take this also. 1, 2, 3, 4. Or maybe, I will shift this on the other side so that we get this space also. This will be black. This is our intermediate. These are albinos. This is fair. This is very fair. This one is dark, and this is very dark. So we get this space also. Okay, so this is our key. Let us write down all these gametes here. So do we have 8? 1, 2, 3, 4, 5, 6, 7, and this gives us the 8. All gametes here, capital. Let's start here. A, B, C, 3 dominant, then A, B dominant, C recessive, then A, C dominant, B recessive, then B, C dominant, A recessive. Then A dominant, B, C recessive, B dominant, A and C recessive. Oh, we are short of space. Let me make one more at the top here. So let us write from here. A, B, C dominant, A dominant, B dominant, C is recessive. A, C dominant, B recessive, B, C dominant, A recessive, and then A, the next two recessive, B dominant, A and C recessive, C dominant, A and B recessive, and here we have all recessive. Same thing here. A, B, C, A, B dominant, C recessive, A and C dominant, B recessive, B and C dominant, A recessive, A dominant, B, C recessive, B dominant, A and C recessive, C dominant, A and B recessive, and here we have A, B and C all recessive. Now we have to fill up all these. The easiest option, or maybe the orthodox option, would be that we write A, B, B, C, C. But, and then it's going to take about half an hour to fill up this complete Punnett square. Instead, can we go for a shortcut using this key? Instead of writing all A, B and C's, can we just write down the number of dominant here? And that is possible. This shortcut is possible only in case of polygenic inheritance. It should not be followed when we are talking about a typical trihybrid Mendelian cross. There the ratio is different. So only in polygenic we will go for a shortcut. We will simply write the number of dominant. Here 3 from here, 3 dominant. Here 3 dominant, 2 from here, so 5. This will also be 5, 3 plus 2. This is 3 plus 2, 5. This is 3 and 1 here, so 4, 4, 4. And here 3 dominant. Let us do here 3 here, 2 here. 5, 5 and 5. 2 and 2 from here, 4, 4. So here it's going to be only 4. This will be 3, 3, 3 and 2. Because here we are talking of only 2 dominant. In this case, 3 plus 2, 5. Let us do it like this. 3 plus 2, 5. 3 plus 1, 4. 3 plus 1, 4. 3 plus 1, 4 and only 3. In this case, 2 and 2, 4. 2 and 2, 4. 2 and 1, 3. 2 and 1, 3. 2 and 1, 3. And here only, 2. Coming from here. In this case, 2 are coming from here and 2 from here. So 4. 2 and 2, 4. 2 and 1, 3. 2 and 1, 3. 2 and 1, 3. And only 2. Now, next one is 2 dominant. 2 dominant here. So 4. 2 and 2, 4. 2 and 2, 4. 2 and 1, 3. 2 and 1, 3. And here, okay, this one is only 2. Here, sorry, this should be 3 because 1 is from here and 2 from here. Here only 1 dominant. So here 2, 2 and 1, 3. This is 1 and 2 from here 3. This is 1 and 1, 2. This is 1 and 1, 2. 1 and 1, 2. And here only 1. Now, let us take this one. 1 dominant from here, 2 from here. So this is 3, 2 plus 1, 3, 1 plus 1, 2, 1 plus 1, 2, 1 plus 1, 2, and here only 1 because there is no dominant from this gamete. In this case, 1 dominant here, 2 here. So 3, 3, 1 and 1, 2, 1 and 1, 2, 1 and 1, 2, and here is going to be 1. Now let us talk about the next one. That is the last one. We have done these two. Here, no dominant, so 2 from here, 2 from here, 1 from here, 1 from here, 1 from here, and 0 from here. No dominant. Now, we will have to find out how many have 6 dominant genes. Here, these two extremes, one is 6 dominant, one is 0 dominant. So we know out of 64, one is going to be with 6 dominant, that means black. One is going to be with no dominant, that is albinos. Now let us see how many 5s do we have. And while making this, we need to be sure that we have written the numbers correctly. Okay, I think we have made one mistake here. Here there are 2 dominant and 2 here, so this should have been 4. And the same thing here. This should also have been 4. I guess we have written all others correctly. Now let us count the 5s. How many 5s we have? That means we are talking about the people who have 5 dominant genes. So let us start from here. 1, 2, 3, 4, 5, 6, and here no 5. So we have 6 individuals with 5 dominant genes. Now let us count how many of them have 4 dominant genes. 4 dominant. So let us start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 individuals who have 4 dominant traits. Now let us come to 3 dominant. 3 dominant. Let us start counting from here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So there are 20 individuals who have 3 dominant. Now 2 dominant. 2 dominant would be, let us start from here. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So we have 15 individuals who have 2 dominant genes. Now let us see how many of them have 1. So here we are all done. So this is 1. 1, 2, 3, 4, 5, and 6. We have 6 individuals with 1, and this one we have already written. Now if we plot a graph, our graph is going to be something like this. The extremes, the number is minimum, and the intermediate, the number is maximum. So here we have 20, this is our maximum number, this is 20. On either side the number is decreasing, that is 15, 15. So we would have 15, 15 here. Again it has gone down. So 6, 6 and this is 1 and 1. So this is known as bell-shaped graph, and this is what we get in case of polygenic inheritance or skin color inheritance. This is a shortcut. Instead of filling it with all alphabets, we can simply write the numbers, but we need to be very, very careful while writing the numbers, because if we make one mistake, the ratio is going to be totally wrong. So this is polygenic inheritance, that is skin color in case of human beings, which was given by Davenport.